Good afternoon. This is October 23rd. This is Calculus 1. Today, our main objective is to finish up our discussion of analyzing graphs using the first and second derivative. But before we get into that, let's first talk about this week and what's going on this week. Today, Monday, I have online office hours. From 8 to 9 p.m. Tomorrow, Tuesday, so that's online today. Tuesday, I have on-campus office hours. And that goes from 4 to 6 p.m. And remember, on campus means I'm going to be at the North Harris campus, and I am in Winship 115K. So as we're heading into exam 2, if you want to come by the office and actually talk to me in person and go over some questions that you've got about the review, that would be a great time to come by and talk to me. Wednesday, I will also be on campus. So I have on-campus office hours. And in this case, it'll be from 11 a.m. to 1 p.m. Once again, please come on by for help if you are available during either of those time periods. Thursday, the exam 2 testing window opens and runs through October the 31st. So you can start taking the exam on Thursday, and you've got through the 31st to take it. An exam 2 review update. I did send an email out today, so hopefully if you check your email, you'll have gotten this update. I did leave one topic off of the exam 2 review that I posted last week. Logarithmic differentiation got left off, and I'm going to cover that on the exam. So I have reposted the review and have put in a last page on logarithmic differentiation. I've also emailed that to everyone, so you should have a copy of the updated review. And the very last page is on logarithmic differentiation and some questions that I will definitely be asking you about on this exam. All right, so let's get into what we're going to be doing today. So today is a graphing summary. We're going to finish it. First of all, and when I say graphing summary so far, it's what we've talked about so far with graphing in the first and second derivative. And then we're going to move into something called the second derivative test and talk about how we use the second derivative to find relative maxes and mins in certain situations. And then we'll look at limits at infinity, look at what happens and how we evaluate limits as x gets arbitrarily large or x gets arbitrarily small, how we evaluate certain limits like that, and what their impacts are on the graph. So we'll be relating this to vertical, horizontal, and slant asymptotes. And then finally kind of tie up some loose ends and have a conclusion to all this discussion on graphing. All right, so we are going to go ahead and kind of jump into that right now. First of all, let's summarize some things we have done with derivatives in graphs. So if we have this function y equals f of x, first thing is we look at the critical numbers for a function. And remember, critical numbers are places where the derivative is equal to 0. So f prime of a is equal to 0, or f prime of a is undefined or does not exist. So critical numbers are places where the derivative is 0 or the derivative does not exist. And if you've got a function that's continuous, but its derivative is equal to 0 or does not exist, then you've got a couple of different situations. Let's just kind of briefly sketch out a few graphs here. First of all, you have the more typical situation at a right there. We have that f prime of a is equal to 0. That is a relative max at a. Here we have a relative minimum at a. F prime is 0 there. And then finally, at a, we could have this situation certainly where f prime is 0, but you have neither a max or a min. So just because you have a critical number, remember, doesn't mean you have a maximum or a minimum. It just means you could have a maximum or a minimum. So those are three good pictures where you have a continuous function. The derivative is equal to 0 in all three pictures. Two of them have extreme values. You have a relative max here. In this picture, you have a relative min in this picture, and then no relative max or min in this picture. All right, and then we have the exact same kind of situation, sort of, with the derivative being undefined. So you have the derivative undefined here at a. So here you have f prime of a does not exist. And what do you have? You have a relative maximum there. And remember, that kind of point is called a cusp. There is a vertical tangent line there. This next graph, and at that point, at x equals a, again, f prime of a does not exist. And here you have a relative minimum. And then, obviously, you could have a vertical tangent line like so, right, at a. And in that situation, f prime of a, that picture, f prime of a does not exist either. And no relative max or min in that case. No relative maximum or minimum. So again, remember that a lot of things could happen. You have to be aware of what you're actually finding when you find critical numbers. Critical numbers are simply potential places where you have a relative maximum or minimum, and they're not. It's not that you know that for sure. What do you look for in a situation like this? You look for a sign change in the derivative. Right? If the derivative function goes from a negative to a positive, it means the function goes from decreasing to increasing, and it means there you get a relative, and let's say at that particular point you get that the derivative is 0 or undefined, so this is a critical number right here. Then you have a relative minimum. If, on the other hand, with f prime, right, you get this critical number here, and the function goes from, the derivative goes from positive to negative, then the function goes from rising to falling, and then you get a relative maximum. Now remember, so what are we looking for? We're looking for sign changes in the derivative, and if we get a sign change in the derivative at a critical number, then we have got a relative maximum or a minimum. Remember, this idea is referred to as the first derivative test. And this is something we were talking about last week, in lecture last week, was trying to build up this idea about the first derivative test. All right. With the second derivative, now we're talking about what I refer to as hypercritical numbers. Remember, that is not a standard terminology for the second derivative, but it's one that I use. And for hypercritical numbers, we're saying that those are places where the second derivative at a is equal to 0, or the second derivative at a does not exist or is undefined. All right, and so what we have seen with the second derivative, if the second derivative is 0, when you get hypercritical numbers, right, you get pictures that look something like these right here. You get a graph, for example, that has a change in the concavity right here, right? This is a point of inflection right here. Right, and you also can get a point of inflection like this. Right, and then in this problem, we would get that the second derivative is equal to 0 at that point. In this one, we would get that the second derivative does not exist. But in either case, you get a point of inflection. And remember the idea here, and again, also remember that Just because the second derivative, for example, does not exist doesn't mean that you have a point of inflection. So at a cusp, like this, right, the second derivative does not exist at a cusp, but there's no point of inflection there. Remember, point of inflection is where the graph has a change in the concavity, right? We know that when the second derivative is positive, you have a graph that's concave up. And when the second derivative is negative, you have a graph that's concave down. All right, and when you get a change in the sign in the second derivative, so draw a number line out, kind of like I did the first derivative. So let's say we have an a here, you have the second derivative goes from positive to negative, then we see that the function goes from concave up to concave down, and you have a point of inflection. Right, at a. And the exact same thing is true, certainly, if at a the sign change goes the other direction. The function changes from concave down to concave up, you still have a point of inflection. Right, so we're looking for places where the concavity of the graph is changing. Right, the second derivative would allow us to do that. All right, so let's kind of work through a problem and kind of go back and review that. I think that would be a good thing to do, is for you to see a little bit more, a few more examples about how we work problems like these. So I'm going to look at this function, negative x cubed plus 6x squared minus 5. And we're going to look at analyzing the graph here using the first and second derivative. So analyze the graph using first and second derivative. Okay, so the first derivative of this function is negative 3x squared plus 12x. And when we factor that, we take out a common factor of negative 3x, and we're left with x minus 4. We go ahead and set the derivative equal to 0, and it's equal to 0, and x is 0, and x is equal to 4, and so those are my critical numbers. These are polynomials, so there's no chance that the derivative is undefined anywhere. Polynomials we know are differentiable everywhere. So the critical numbers are at x equals 0 and x equals 4. All right, so we analyze the sign of the derivative at or around those critical numbers. So here's 0, here's 4, and then I pick test values in between. So I might pick x equals negative 1, x equals 1, x equals 5. Any numbers, any real numbers in those intervals would be fine to check. So when you substitute negative 1 in, when you look at f prime at negative 1, and remember that's what you're doing, you're looking at f prime of negative 1, f prime at 1, and f prime at 5. You're looking at the derivative evaluated at those test numbers. So the derivative evaluated at negative 1 would give you a positive factor times a negative factor if you're looking at the factored form of the derivative, and so the derivative would be negative there. F prime at 1 would give you a negative factor times a negative factor right there, and so the derivative would be positive. And then f prime of 5 would give you a negative factor times a positive factor, and that would give you a negative. So this tells us that the function is decreasing less than 0, increasing between 0 and 4, and then decreasing again from 4 and larger, 4 to infinity. So writing out those intervals, we get that the function is increasing from 0 to 4, and it is decreasing from negative infinity to 0, and then from 4 to infinity. We get a relative maximum based on the first derivative test. There's a sign change at 4 that goes from positive to negative, increasing to decreasing. That's a relative maximum. at 4. And remember, now to find the y value, you find f of 4, and f of 4 would be equal to 27. Doing the arithmetic there, and you certainly should check my arithmetic, but I'm pretty sure that's okay. So relative max is 427. Remember, go to the original function to find that 27. Don't substitute 4 into the derivative. That doesn't do you any good. You're trying to find points on the graph of the function. And so the function is negative x cubed plus 6x squared minus 5. Relative minimum, there's a sign change at 0, and the function goes from decreasing to increasing. So there's a relative minimum at 0, and then substitute that in. That's easier to calculate, certainly, and you get negative 5 for the y value. So those are my relative maxes and mins. All right, so now let's go to the second derivative and analyze the second derivative. So f double prime of x is negative 6x plus 12. You can factor that. Take out a common factor of negative 6, and you'll be left with x minus 2. So the second derivative is equal to 0 when x is equal to 2. Right? And so that's my hypercritical number. Remember, we don't have to worry about the second derivative being undefined because this is a polynomial function. So these derivatives are defined everywhere. The hypercritical number here is at x equals 2. And so now we analyze the sign of the second derivative around that hypercritical number around 2. We pick a couple of x values for test values. We might pick x equals 0. I always try to pick x equals 0 when I can. And then x equals 3 for my test values. And I'm looking at f double prime at 0 and f double prime at 3. You're looking at whether that's positive or negative. So f double prime is 0. You have a negative 6 times x minus 2. So that's a negative times a negative. And so the second derivative is going to be positive, less than 2. And then when you substitute in 3, you get a negative because of that negative 6 times a positive. And so you get that the function is concave down, right? That the derivative is, a second derivative is negative. So you have the functions concave up and then concave down. And so then we can summarize this information. The graph is concave up from negative infinity to 2 and concave down from 2 to infinity. There is a sign change in the second derivative at 2. The concavity is changing there, and so that is a point of inflection in the graph, a place where the concavity changes. And the point of inflection would be at 2, and then you have to find the y value. And remember, once again, go to the original function to find that y value, right? That's the graph that you're looking at, not the graph of the first or second derivative. You're looking at the graph of the original function. So f of 2 is equal to 11, I believe. Okay, so that's a nice little summary of some of the things that we've talked about. I do want to work one more problem, kind of looked at this in a slightly different way to make sure that everybody, again, is okay. So one more example, and this is frequently, or this is not uncommon for me to do this on an exam, to what I'm about to do in this problem. So I may give you a function, f of x equals x minus 2 cubed times x minus 1, let's say. And I may actually also give you the derivative and the second derivative as well. So I may give you that the first derivative is x minus 2 squared times 4x minus 5, which it is, and that the second derivative is 6 times x minus 2 times 2x minus 3. So I may give you the function, the derivative of the function, and the second derivative of the function, and then ask you to analyze the graph. So same analysis that we've just looked at, right? You've got f prime is x minus 2 squared times 4x minus 5. And so that gives us that there are critical numbers, places where the derivative is 0, at x equals 2 and x equals 5/4. All right, and then right alongside that, the second derivative is 6 times x minus 2 times 2x minus 3. And so we could identify hypercritical numbers. at x equals 2 and x equals 3/2. Those are my hypercritical numbers. And so then we go through a similar analysis that we've just been talking about. So we analyze the sign of the first derivative around the critical numbers. So I put 5/4 here and 2 here. I pick out test values in between those critical numbers. So I might pick x equals 0 and x equals 1.5 or 3/2 and x equals 3. Remember, you are now checking the sign of the derivative. So you're looking at f prime of 0, f prime at 1.5, and f prime at 3 to see what the sign of that value is. So f prime of 0, now x minus 2 squared, you're looking at the derivative there, and x minus 2 squared is always positive because it's a square. So that's a positive times a negative. And so the first derivative is negative. F prime at 1, well, x minus 2 squared, again, is always positive. But then when you substitute 3/2 in for 4x minus 5, you get a positive there also. And so the derivative is going to be positive. And then finally, you look at f prime of 3, and you have a positive times a positive again. And so the first derivative is positive there. So what do we have? That the function is decreasing less than 5/4. It's increasing between 5/4 and 2, and it's still increasing greater than 2. Okay, so the let's see, what do we have here? We have that the function is increasing from 5/4 to 2 and from 2 to infinity. And the function is decreasing from negative infinity to 5/4. We do not have a relative maximum. So I'll write relative maximum here, but I'll write none because there's no place where the graph goes from rising to falling, where the derivative goes from positive to negative. And then a relative minimum. Well, the relative minimum here is at 5/4. And I will leave it up to you to find the y value there. But remember that 5/4, well, let's see, I think we can actually probably do that without too much difficulty. F of 5/4, remember, go to the original function. So that's 5/4 minus 2 cubed, and then that's times 5/4 minus 1. So 5/4 minus 2, that's 5/4 minus 8/4, which is negative 3/4, and then you cube it, and you get negative 27 over 64. And then 5/4 minus 1, that's 5/4 minus 4/4, which would be 1/4. So this is times 1/4 right here. And so you get negative 27 over 256. Okay, so that's our relative minimum. Negative 27 over 256, like that. All right, the second derivative. Let's go through the analysis of the second derivative. So now the hypercritical numbers, and I've already calculated the second derivative for you. So the hypercritical numbers are going to be at x equals 2 and at x equals 3/2. And so our analysis of the signs, we put 3/2 and 2 on the number line. We look at the second derivative. We pick out test numbers in each of these intervals. You get x equals 0, x equals 1.75, 1 3/4, 7/4, and then finally x equals 3. And so now we look at the sign of the second derivative at 0, and the sign of the second derivative at 1.75, and the sign of the second derivative at 3. The sign of the second derivative at 0, you get two negatives multiplied together there. If you look at the factors for the second derivative, the 6 is positive, so it doesn't really affect anything. So you're just looking at the x minus 2 and the 2x minus 3. So you get that the second derivative is positive. And then at 1.75, you substitute, and x minus 2 is going to be negative, and 2x minus 3 is going to be positive. And so you get a negative for the second derivative there. And then greater than 2, you could pick x equals, you pick 3, you test 3, f double prime at 3. You have 2 factors that are positive there, and so the second derivative is positive. So we get the function is concave up, less than 3/2, concave down, between 3/2 and 2, concave up, greater than 2. And so we summarize that information, and you get that the function, let's see, we'll write that the function is concave up from negative infinity to 3/2, and then from 2 to infinity. We get that the function is concave down from 3/2 to 2. We get points of inflection. We have 2 sign changes, so we have 2 points of inflection. One of them is at 3/2, and then the other one is at 2. Now 2 is easy to calculate. That's just 0 for the y value. But the y value for 3/2, you're looking at f of 3/2. And so you get 3/2 minus 2 cubed times 3/2 minus 1. So let's see, 3/2 minus 4/2 is negative 1/2. And then cubed would be negative 1/8. And then 3/2 minus 1 would be 3/2 minus 2/2, or 1/2. So you get negative 1/16 for the y value there. Always forget, don't forget to go to the original function when you're finding those y values. Okay, so that's a nice little summary of those 2 pages. Hopefully kind of draw together what we've been talking about with graphs and kind of looking over the first derivative and the second derivative. All right, now, the second derivative in particular can also be used sometimes to look at relative maxes and mins. Now, going back to these 2 problems one more time, what did we do here? We see that the second derivative was associated with concavity, and the first derivative was associated with relative maxes and mins, right? First derivative right here associated with relative maxes, relative mins, and then the second derivative here and associated with concavity for the function. Now, for using the first derivative test, that's certainly true. But the second derivative test is another way of dealing with the second derivative called the second derivative test. And the second derivative test is a way to use f double prime to look at relative maxes and mins. Okay, so how does this work? How does it work? First thing is, if you think about a relative maximum where the derivative is 0, right? We know that f prime here at a is equal to 0. Notice that around x equals a, this function is concave down, right? That if you look at the sign of the second derivative now, remember this is the graph of the function, so the sign of the second derivative here would be negative in this interval, right? So what we're seeing here is that if you get that the first derivative of a function is 0 and the second derivative at some value a is negative, then you have a relative maximum, right? So this is a way of taking a critical number where the derivative is 0 and the fact that the second derivative is negative to conclude that you must have a relative maximum at a. And a similar picture, right? If you have a graph that looks like this at a, right? This is our function f. What do we see here? That f prime at a certainly is 0. But now what about the signs of the second derivative? Now the second derivative is positive around x equals a. So what do we have here? That if the first derivative is 0 and the second derivative is positive, then you have a relative minimum at x equals a. This page is summarizing the second, what we call the second derivative test. It's a way of looking at the second derivative and using it to analyze where you have maxes and mins. Notice the second derivative test cannot be used. It cannot be used to find relative maxes and mins where f prime of a is undefined. Right? This only applies to places where you have a horizontal tangent line. All right, so let's look at an example of the second derivative test. So let's say we have this function, f of x equals negative x cubed plus 7x squared minus 15x. And I want to use the second derivative test to find all relative extreme values. Now this is a polynomial, so the second derivative test could be used here because the second derivative is going to be defined. There's no place where the first derivative is undefined here. And so we don't have to worry about those kinds of maxes or mins. We don't have to worry about cusps here at all. All we're worried about are these nice smooth maxes and mins where the derivative is equal to 0. And so that's the first thing you do, is you first find, so this is step one, first find where f prime is equal to 0. So in our function, f prime of x is negative 3x squared plus 14x minus 15. Now you can factor out a negative 1 out of that, which is what I would do, which gives me 3x squared minus 14x plus 15. And that is a factorable polynomial, which is nice. Put a 3x here and an x here, and you get 3x minus 5, x minus 3. And let's see. Okay, so you have 3x minus 5 times x minus 3, and that would give you the 14x that you need as the middle term. So f prime is equal to 0 when x is 5/3 and x is 3. The second step, look at the sign of f double prime at 5/3 and f double prime at 3. So find the second derivative and see whether the second derivative is positive or negative at places where the derivative is 0. Right? So we find the second derivative. So f double prime in our problem is going to be negative 6x plus 14. And so then we look at f double prime at 5/3, which would be negative 6 times 5/3 plus 14. Negative 6 times 5/3 is negative 10, so this ends up giving you 4. So what do we have here? That f double prime at 5/3 is positive. F double prime at 3 is negative 6 times 3 plus 14. So it's negative 18 plus 14, or negative 4. And so you have f double prime at 3 is negative. And so what do we have here? We have that f prime at 5/3 is 0, and f double prime at 5/3 is positive, and that means we have a relative minimum at 5/3, right? We have a relative minimum at 5/3. The function's concave up, and you have a horizontal tangent line. So if you think about the way the graph has to be shaped, you would have to have a relative minimum there at 5/3. And then f prime at 3 is equal to 0, and the second derivative at 3 is negative. So this is a function where you have a horizontal tangent line, but the function's concave down. So the only conclusion there is that you have a relative maximum, and that relative maximum would be at 3. Don't forget how you find the y values there. You have to find f at 5/3, just like you did with the first derivative test, and f at 3. So you have to find those to find the y values there. All right, which I'll let you do. So that's how you can use the second derivative to analyze whether you have relative maxes or mins. Okay, so I will not ask anything about the second derivative test on this exam, on exam 2 that's coming up this week, but I may ask you about the second derivative test going into exam 3. All right, so now we're ready to turn our attention to end behavior of graphs, limits at infinity, asymptotes. So end behavior, limits at infinity, and asymptotes. So we're looking at some other features of graphs and going to be combining this with calculus also as we go through our discussion. So let's first of all kind of start looking at some things about end behavior and asymptotes, things like that. So let's just do this by drawing some pictures, first of all. So if we have a graph of a function, and let's say that this graph has a horizontal asymptote at y equals 1, and let's say it has another horizontal asymptote at y equals -1. Now, rational functions, it's common for rational functions to have asymptotes, horizontal asymptotes, but rational functions would never have 2 horizontal asymptotes. They can only have 1 horizontal asymptote. Nevertheless, there are some types of functions that can have 2. All right, let's say that our graph for our function looks like something like this. Now this graph, notice it actually crosses through one of the horizontal asymptotes. That's okay to happen. And what I'm looking at in particular is what does this graph do when you're looking at the limit as x goes to infinity? In other words, as x gets larger and larger, what is the y value doing? Right, so as you move down the x-axis and pick larger and larger x values, so notice I'm picking x values moving on down the x-axis like this. What does the y value do? And we can see that there's a horizontal asymptote there, and so that the y value is simply just getting closer and closer to 1 in this case. Right, and so we say that the limit at infinity for this function is 1. The function gets arbitrarily close to 1 as, or the y value gets arbitrarily close to 1 as x gets arbitrarily large. And what happens as you move off to the left, the limit at -infinity? Excuse me. So the limit at -infinity, so you're moving off to the left, and so now I'll put these little marks in blue here. Now we're moving off to the left forever in that direction. And what's happening here, well, now the function actually crossed through the asymptote there, but the y value is getting closer and closer to -1 as the x value is getting to be a larger and larger negative number. And so we say that this is -1 right here. All right, so one thing that this graph kind of illustrates here is that if the limit as x goes to infinity of f of x is equal to some constant, or the limit as x goes to -infinity of some function goes to a constant, right? That implies here that you have a horizontal asymptote at k. right? The limits at infinity and horizontal asymptotes go together in that respect. Now you can have all sorts of different things happening on a graph, all sorts of different scenarios, all sorts of different combinations. So let's say we have a graph that looks like this. We have a horizontal line right here at y equals 2. At y equals 2. And we get that this graph kind of looks like this. It's definitely a different shaped graph. This one actually crosses through its horizontal asymptote an infinite number of times. So you have a graph that kind of starts oscillating around the asymptote at y equals 2. So what do we have here on the graph? We have the limit as x goes to infinity of f of x. Now I know the graph's oscillating around y equals 2 as the x values get larger and larger, but what I want you to notice is that those oscillations kind of get tighter and tighter and tighter around y equals 2. And so in fact this limit at infinity would be equal to 2. And there is a horizontal asymptote, and the graph can behave this way around a horizontal asymptote. Now the limit as x goes to negative infinity, as you go off to the left in this graph, well, notice as you move off to the left, right, you're moving over here, x going to negative infinity. Well, in this case, what's happening? The y value is just getting larger and larger right here. And so this limit at negative infinity is equal to infinity. We still have a horizontal asymptote here, no question about that. Horizontal asymptote at y equals 2, but it's only approaching that asymptote as you move off to the right, not as you move off to the left. Right? One last little picture on this page. We have a function that has a horizontal line. Let's see, this horizontal line is at y equals 5, we'll say. And the graph looks like this. So what's going on? This is definitely a horizontal asymptote. We have the limit as x goes to infinity. As you move off to the right on the x-axis, the y value in this function is getting closer and closer to 5. That's our horizontal asymptote. In the limit as x goes to negative infinity for this function, as you move off to the left, right, you're going off in this direction. X is going to negative infinity. Notice that the y value is just shooting down. The y value is going to be a bigger and bigger negative number, and so this would be negative infinity. All right, so once again, horizontal asymptotes are tied closely with limits at infinity. All right. On the next screen, let's say we have that if we're looking at the limit as x goes to positive or negative infinity and of some function, and we see that that is going to a constant in the numerator and either positive or negative infinity in the denominator. So in other words, you've got some function when if you pick bigger and bigger x values or smaller and smaller x values, you get a constant in the numerator or approaching a constant in the numerator, and the denominator is getting large without bound, either in the positive or negative direction. This limit is always got a value of 0. So if the function is going to a constant in the numerator, infinity or negative infinity in the denominator, you're going to get 0 as the value of the limit. So as an example here, if you have the limit as x goes to infinity of 2 over x, let's do something simple. So what have we got here? That the numerator is actually always 2 here. It's a constant, but the denominator is getting large without bound. And so what do we have here? This is an example of the form that we saw at the top of the screen here. That limit is 0. Right? 2 over a number that's getting larger and larger and larger is going to get closer and closer to 0. All right, if we have the limit as x goes to negative infinity of negative 3 over x cubed. All right, so what do we have here in the denominator? in the denominator, the expression is a constant, so it's always -3. And that's the numerator. I'm sorry, the numerator is a constant. In the denominator, as x gets to be a larger and larger negative number, when you cube it, that's going to be a larger and larger negative. So that's going to -infinity. And so it doesn't matter whether it's -infinity or positive infinity. It doesn't matter whether the numerator is a positive real number or a negative real number that it's approaching. You're going to get 0, right? If the denominator is getting big without bound and the numerator is a constant, this is going to go to 0. All right. The limit as x goes to infinity of x to the 5th minus 2x cubed plus 3x squared minus 8x plus 7. Now what I want to point out here is that when you have powers of x and you have a limit at infinity, whether it's positive infinity or negative infinity, that ultimately the only term that really matters is the term with the biggest power, that it completely dominates the other terms. And so x to the 5th is the dominant term here. In other words, it controls that term, and when I say it, I'll say that term controls the end behavior of this function. It doesn't matter what the other terms are ultimately. When x gets large, the only term that matters is the x to the 5th term. All the other terms, even though they may be really big for a specific x value, x to the 5th is going to be much, much larger. And remember, this is only when we're talking about x at infinity. X is getting larger and larger and larger. So the x to the 5th dominates this term, and x to the 5th is going to infinity. And so that's what this limit is. This limit's infinity right here. All right? All you're doing really here is looking at the limit as x goes to infinity of the dominant term, which is x to the 5th. And that's infinity. That's getting arbitrarily large in the positive direction. All right. The limit as x decreases without bound of x to the 5th minus 2x cubed plus 3x squared minus 8x plus 7. Same function, but now we're talking about the limit as x decreases without bound. X to the 5th, it's a limit at infinity. And so x to the 5th is the dominant term. And what do we have here? That as x gets large in the negative direction, as x goes to negative infinity, right, what does x to the 5th do? Well, you're talking about a bigger and bigger and bigger negative number, raising it to the 5th power. That's negative. And so that's negative infinity here. So this limit is negative infinity. Right? It's because this ended up being an odd degree term. Or an odd degree dominant term, I should say. If you had the limit as x goes to negative infinity of 2x to the 4th minus 8x cubed minus 9x squared minus 10, like that, the dominant term in this case is the 2x to the 4th. The 2x to the 4th is the dominant term. Again, as x gets larger and larger and larger and larger in the negative direction, because this is the limit as x goes to negative infinity, the x cubed term, the x squared term, the negative 10 term, none of those matter. The only term that really ultimately matters for large x values is the 2x to the 4th. It completely dominates the other terms. But what's going on here? The x is going to negative infinity, so x is negative, but I'm raising it to the 4th power. So you end up with a positive number there, and that's positive infinity. Let me erase that real quick because it looked like a negative infinity when I wrote it, but this is positive infinity. But the x to the 4th term is controlling that. And since it's an even power, right, you're ending up with a positive infinity for the value. All right, next example as we move through here and look at some examples of limits at infinity. Let's say we have the limit as x goes to infinity, now not of a polynomial function, but of a rational function. So what I want you to look at here, this is a limited infinity, so, and these are polynomials in the numerator and the denominator, so we can talk about the dominant terms here. And the dominant term in the numerator is x to the fourth, and the dominant term in the denominator is 3x to the fourth. And so looking at the dominant terms here, in the top and the bottoms, we see that this fraction, as x gets large, is going to get closer and closer to just x to the fourth over 3x to the fourth. None of the other terms will matter as x gets larger and larger. And then what about x to the fourths there? Those x to the fourths would cancel, and so you'd end up with the graph getting closer and closer to 1/3 here. So the value of this limit is 1/3. And what this shows here is that this graph, the graph has a horizontal asymptote at y equals 1/3. Remember, these limits at infinity, if they exist, are indicating that you have a horizontal asymptote on the graph. All right, now, and there's an alternate way of looking at this kind of problem that I want to show you. Some of you may have seen this other technique before. So an alternate method for evaluating a limit like this one is to divide the numerator and denominator by the largest power of x. That appears anywhere in the expression. So in this case, the largest power of x that appears anywhere in the expression is x to the fourth. And so what you're doing here with this alternate technique for evaluating a limit like this is you're multiplying top and bottom by 1 over x to the fourth. In other words, you're dividing every term by x to the fourth here. And so this is just the distributive property, and like I said, you're dividing every term by x to the fourth. And so what happens is you get the limit as x goes to infinity, and then divide every term by x to the fourth. So this would be 1 minus 2 over x plus 3 over x cubed minus 1 over x to the fourth in the numerator. And then in the denominator, you'd have 3 minus 2 over x squared plus 8 over x cubed plus 6 over x to the fourth. So you have the limit of that expression, and that looks like a mess. I understand that, but what I want you to look at is as x gets large, if you're looking at the limits of all those little fractions in there, notice that the limit, like for example, the limit as x goes to infinity of 2 over x is just 0. And the limit as x goes to infinity of 3 over x cubed is equal to 0, etc. Right? In other words, the limit of all, as x goes to infinity, of all those little fractions that are sitting inside that bigger fraction, those are all going to 0. Every one of them. And if you throw away all those terms, what are you left with? Sure enough, you're left with 1/3, which is what we found with this kind of dominant term method for looking at these types of limits or these types of functions. Now, this alternate method certainly looks messier than the first method, the dominant term method, and it certainly is in this context. But it may be certain situations where you have to use the alternate method, and you'll see that in a few minutes. All right, so let's look at another example, and let's go back to the dominant term method. So if we have the limit as x goes to infinity of x squared minus 8x plus 4 over x, let's say 8x cubed minus 27. So in this case, what are the dominant terms? The dominant terms are in the numerator x squared and in the denominator 8x cubed. And so what happens? The x's divide out there and you're left with 1 over 8x. And remember that the x value is getting to be larger and larger and larger without bound. It's going to infinity. So this is going to 1 over infinity. This is going to 0. So you get the value of 0 for this limit. Now, if you had done the same thing with the alternate method, same problem with the alternate method, then what you're doing here is you're dividing every term by the largest power of x. And the largest power of x would be 1 over x cubed. And so you're multiplying top and bottom by 1 over x cubed. And so that would give you 1 over x minus 8 over x squared plus 4 over x cubed. That would be the numerator. And the denominator would be 8 minus 27 over x cubed. And then what happens? All the little fractions go to 0, right? Every one of these little fractions goes to 0. And what are you left with when that happens? You're left with 0 in the numerator and 8 in the denominator. You get the value 0 for the limit. So you get the same answer, you just get it a different way of reasoning it to get to 0. All right. Now, what I want you to see as we're going through these examples is that on this page, I was looking at a rational expression where the numerator and the denominator had the same degree. They were both degree 4, and how both of these methods work for evaluating this type of limit. On this page so far, the first example, I've looked at both methods again. But I'm looking at what happens when the degree of the numerator is less than the degree of the denominator. So now let's look at these same kinds of limits, but now let's look at the limit of the numerator being larger than the denominator. So let's say we have x to the 4th plus 6x minus 1 over x cubed minus x squared plus 2. And notice the degree of the numerator is bigger than the degree of the denominator. All right, with the dominant term method, right, the dominant term in the numerator is x to the 4th, and the denominator is x cubed, and so you get x, right? You have x to the 4th over x cubed, so you get x over 1, or x. And as x gets large, what does that do? That goes to infinity. And so this limit's equal to infinity, right? It means there's no horizontal asymptote. On the first page, or the first problem on this screen, you had a horizontal asymptote at 0, based on what we got as the answers to those limits. In this case, no horizontal asymptote at all. So, and probably should have written that in there. So in this case, you have a horizontal asymptote at y equals 0. And in this problem, no horizontal asymptote, because there's no value for the limit at infinity. Remember, these are all limits at infinity we're talking about. With the alternate method, you're dividing everything by x to the 4th, because that's the largest power of x. So you're going to have 1 over x to the 4th and 1 over x to the 4th. And when you do that, you get the limit as x goes to infinity of 1 plus 6 over x cubed minus 1 over x to the 4th, all over 1 over x minus 1 over x squared plus 2 over x to the 4th. And so what do we get here in this case? All the little bitty fractions inside go to 0. Let me put that in red there. These all go to 0. But notice all of them in the denominator go to 0 now. Every term does. And so what do we get? We have a situation here where the denominator is going to 0 and the numerator is going to 1. And that's a case when, remember, when the denominator is going to 0 and the numerator is going to a constant, then you are getting either infinity or negative infinity as the answer. In this case, you get infinity as the answer. And same answer that we got with the dominant term method. So no horizontal asymptote in this case. All right, so now in the next example, this dominant term method, maybe let's see how we can apply that here. So this next example, we have the limit as x goes to infinity of the square root of x squared plus 1 over 3x minus 5. And so if you're looking at the dominant term here, as x gets large without bound, the dominant term in the numerator is the x squared. And the dominant term in the denominator is the 3x. But now be careful. You have the 3x in the denominator with the numerator. That's the square root of x squared, not just x squared. Right? X squared is the dominant term, so that's the one we're concerned with. And what's true, if x is going to infinity, x has got to be greater than or equal to 0. And so if that's true, the square root of x squared is x. As long as x is greater than or equal to 0, that's legal to say that. And so what do you get here? That this is x over 3x, or 1/3. Okay? Now you could use dividing by the largest powers of x here, but in this case, the largest power of x that you'd be dividing by would be x. And you'd have to worry about the radical a little bit as far as how you divide that out, and it would be trickier to do. A lot trickier to do, actually. So the limit, let's look at the limit as x goes to negative infinity. So you have the square root of x squared plus 1 over 3x minus 5. Doesn't matter that x is going to negative infinity. This is still a dominant term situation here. So in the numerator, you get the square root of x squared. The denominator, you get 3x for the dominant terms. But now you have to be careful, very careful. X is less than 0 here. Right, x is negative. And because x is negative, what about the square root of x squared? If x is negative, the square root of x squared is the opposite of x. It's not equal to x. It's equal to the opposite of x. Because it's got to be equal to a positive number. But x is negative. So negative x is positive. So what do we get up here? We get that the square root of x squared is negative x. Then you get it over 3x. And that ends up giving you negative 1/3. So notice this graph has a horizontal asymptote at y equals 1/3, and it has a horizontal asymptote at y equals negative 1/3. Right, this graph has two horizontal asymptotes. Okay, so that's something certainly you need to kind of be certainly be aware of and be careful about. All right, so we've talked about limits at infinity, horizontal asymptotes. We need to finish class today talking about vertical asymptotes and slant asymptotes. All right, so vertical asymptotes. And we've talked about this before, so it's just kind of to give completeness here. But vertical asymptotes occur when you have division by 0. And so when you get a fraction where you have a k value in the numerator and 0 in the denominator, and k is not equal to 0. When you get 0 over 0, you may not have you don't have a vertical asymptote. But when you get k over 0, then you get a vertical asymptote for a function. So as an example, if you have f of x equals x minus 1 over x squared minus 4. What do we see here? That f of 2, if you, certainly you could factor the denominator, x plus 2 times x minus 2. And what happens? F of 2 is equal to 1 over 0, right? And that's the situation where you get a vertical asymptote. So there's a vertical asymptote at x equals 2. f of negative 2 gives you negative 3 over 0 when you try to evaluate that. And so there's a vertical asymptote at x equals negative 2 also. All right, so you're looking at where the denominator is 0. Now, if you get a function like this, let's say we have f of x is x minus 5 over x squared minus 6x plus 5, right? You would probably try to factor, and the denominator factors x minus 5 times x plus 1. I'm sorry, not x plus 1, x minus 1 there also. That's better. And so what do we have here? We have that f of 1 gives you negative 4 over 0 when you try to evaluate it. And so what do you have here? You have a vertical asymptote at x equals 1. And now look what happens when you have f of 5. F of 5 gives you 0 divided by 0. When you get 0 divided by 0, you have a hole at x equals 5, right? So 0 over 0 gives you a hole in the graph. All right, so I wanted to kind of mention that again about vertical asymptotes to kind of remind you that you're looking at where the denominator is 0 and the numerator is not 0. Right? So when you've got that a function is going to be equal to a constant over 0 and the constant's not 0, the k value is not 0, then you have a vertical asymptote. If on the other hand you get 0 over 0, you have a hole. All right, so now let's finish this discussion with slant asymptotes. So we've seen now that limits at infinity are refer to horizontal asymptotes, that where the denominator is 0 and the numerator is not 0, you're talking about vertical asymptotes. You're talking about restricted values for the domain of the function. And so now finally let's talk about slant asymptotes. So a slant asymptote occurs where the slant asymptote occurs when the degree of the numerator is exactly 1 more than the degree of the denominator. And let me show you what I'm talking about there as far as the degree of the numerator and the degree of the denominator. Okay, so let's say we have this function f of x is x squared minus 4x plus 6 divided by x minus 3. All right, in that situation, what do we have? We have that the degree of the numerator is 2. The degree of the denominator is 1. And so we have a case where the degree of the numerator is exactly 1 more than the degree of the denominator. This graph has a slant asymptote. By the way, it also has a vertical asymptote, doesn't it? Because f of 3 is 9 minus 12 plus 6 over 3 minus 3. So that's 3 over 0. And so that gives you a vertical asymptote at x equals 3. But there's a slant asymptote. So where is the slant asymptote? Where is the slant asymptote? All right, so what you do is you actually divide this division problem that you have, x squared minus 4x plus 6 over x minus 3. You actually divide this out. Now, in this particular case, you could use synthetic division, but in general, synthetic division is not always going to work here. So I'll go through long division. And a lot of you write long division out in various different ways. So let me show you how I write out long division and how that would help us with what the slant asymptote is. So you take the x squared right? The first term, and you divide it by the first term, x squared divided by x, the dividend divided by the divisor, and you get x. So that would give you, and then you multiply, you get x squared minus 3x. And then remember, you subtract here. So x squared minus x squared is 0. Negative 4x plus 3x is negative x. And then you take first term of the dividend that's left, divided by the divisor, negative x divided by x, and you get negative 1. And so that, when you multiply there, you get negative x plus 3. You subtract, and you get negative x plus x is 0, and 6 minus 3 is 3. So what you're saying here is that in this function, that we could rewrite this as the as the quotient rather, which is x minus 1 plus the remainder 3 over the divisor. That our functions really could be written that way. And now what I want you to notice is that the limit, if you look at the limit as x goes to infinity of the second way I wrote this function, what happens, you get one of those little fractions in there at the end, that 3 over x minus 3. As x is going to infinity, you get 3 over infinity. That is going to 0. And so what's happening here is that x minus 1 plus 3 over x minus 3, that expression, so x minus 1 plus 3 over x minus 3 is approaching just x minus 1 as x gets large. Or small, by the way, so negative infinity also there. And so what do we have? We have a slant asymptote in this graph at y equals x minus 1. In other words, just the linear piece that's left is the slant asymptote for the graph. Okay, so now let's go ahead and draw all this together in a problem that kind of puts together all this discussion we've had about asymptotes with limits at infinity, and also with relative maxes and mins and points of inflection and all that. So let's look at this function. And so we have this function, f of x equals x squared minus 2x plus 1 over x plus 1. Okay, so first of all, we see that as far as vertical asymptotes, that f of negative 1 gives us 0 in the denominator, and in the numerator you get 1 plus 2 plus 1, you get 4. And so you definitely do have a vertical asymptote at x equals negative 1. Horizontal asymptote, you'd be looking at the limit as x goes to infinity. And we see that if we use the dominant terms, we get x squared over x, which is just x, and that goes to infinity, and we see no horizontal asymptote. Now, we could have also seen that by the fact that because the degrees of the numerator and the denominator, the degree of the numerator was 1 bigger than the degree of the denominator. Degree of the numerator is 1 bigger, 1 more than the degree of the denominator. We could have seen here that we were going to get a slant asymptote, and that would have kind of precluded with a rational function us getting a horizontal asymptote. Okay, so there is a slant asymptote. So we find that just by the way we found it on the last page. We long divide this. So you have x plus 1 divided into x squared minus 2x plus 1. And so then we go through the division. You have x squared divided by x is x. So you get x squared plus x. You subtract, and you get negative 3x. Bring down the 1. Then take negative 3x and divide it by x, and you get negative 3. So that's the next term of my quotient. And you get negative 3x minus 3. You subtract, and you get 4. And so in our function, x squared minus 2x plus 1 over x plus 1, we see that we could rewrite it using this division problem as x minus 3 plus 4 over x plus 1. And what happens here, the limit as x goes to infinity for this function is equal to the limit as x goes to infinity of this expression x minus 3 plus 4 over x plus 1. And what happens, that 4 over x plus 1, that little fraction at the end goes away. And then, in fact, this thing is just approaching x minus 3. And so we have a slant asymptote at y equals x minus 3. So we get a slant asymptote at x minus 3. We have a vertical asymptote here at -1. And then we have no horizontal asymptote. So we've kind of got a nice little analysis of the asymptotes there for the function. All right, so now let's go to the derivatives. Let me go ahead and write our function down again. F of x is x squared minus 2x plus 1 over x plus 1. And I've gone ahead and calculated the derivatives already here. So f prime of x is x squared plus 2x minus 3 over x plus 1 squared. And you could certainly factor that as x plus 3 times x minus 1 over x plus 1 squared. And the second derivative for this function is actually a simpler expression. It's 8 over x plus 1 cubed. All right, so let's go through our little sign analysis here. So when we're looking at the derivative, f prime of x is x plus 3 times x minus 1 over x plus 1 squared. That's our derivative. The critical numbers. From the numerator, we get x equals -3 and x equals 1. Those are places where the derivative is 0. The derivative is undefined at x equals -1. Now that cannot be a relative max or a min because that's a vertical asymptote. So we'll still include it in our sign analysis, but it is not a possibility for a max or a min because we know that there's a vertical asymptote there. So we look at the signs of our derivative, and so the signs of our derivative, we put our all of our critical numbers on here. So you have -3. We're going to include -1 and 1. And so the test values in between those intervals, or inside those intervals, would be x equals -4, x equals -2, x equals 0, and then finally x equals 2. So we're looking at the sign of the derivative at -4, the sign of the derivative at -2, the sign of the derivative at 0, and the sign of the derivative at 2. And if you go through that analysis, you'll find that the derivative is positive, negative, negative, positive. And so the function is rising and then falling, and then continues to fall and then rise, like that. And then so summarizing that information, we have that the function is increasing from -infinity to -3 and from 1 to infinity. And it's decreasing from -3 to -1 and from -1 to 1. And then there's a relative maximum at -3, right? Because the function goes from rising to falling there, and the function is defined at -3. And you find the y value. Remember, you find the y value by looking at f of -3. F of -3 here is 8, by the way. So this is -3. I'm sorry, -8. And then the relative minimum does occur. There is one at 1. The function's defined there, but the derivative has a sign change at 1. And f of 1 is 0. And so you have a relative minimum at 1, 0. All right, the second derivative. Not as much to check there at all. So you have 8 over x plus 1 cubed. Right? When we're talking about the hypercritical numbers, the only thing we have to worry about is that f double prime does not exist at x equals -1. Now again, that's a vertical asymptote, so it can't be a point of inflection. But as far as the analysis, we would include it to see whether the second derivative changes sign, to see if we get a concavity change there. So we just have -1 on our axis for the second derivative. We choose a value less than that for a test number, so that would be -2 and greater, and you get 0. At -2, the second derivative is negative. Remember, you're looking at the second derivative evaluated at -2. And then the second derivative evaluated at 0 is positive. So the function goes from concave down to concave up. And so the function is concave up from -1 to infinity, and concave down from -infinity to -1. And there are no points of inflection. There is a sign change in the second derivative at -1, but remember that's a vertical asymptote, so it cannot be a point of inflection. And so that's our nice little analysis right there. If you put this information together on a graph, what you would find is that the shape of the graph, let's see, let's kind of mark some of this information and actually see what we can come up with just by hand drawing the graph rather than going to any technology here. All right, so we have a vertical asymptote at -1. So let's see, so our vertical asymptote's here at -1. We have a horizontal asymptote at y equals x minus 3. So it has an intercept at -3 and has a slope of 1. So here is our slant asymptote, like so. All right. And then what do we have? We have a relative maximum at -3, -8. Let's see. So -3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. Here's -3, -8. We have a relative maximum there. We also have that the function is concave down, right, to the left of -1. And then we have a relative minimum at 1, 0 at this point right here. You could also, if you wanted to, you could look at the fact that there's a y-intercept at 0, 1 as well, if you wanted that to help you. And you get that this graph is concave up here, has a minimum at 1, 0, and you have these asymptotes like this. So you get a branch that looks like this, and then you get a branch that looks like this, right? And that all fits together really well with the information that I found. So we have a decent little sketch of the graph. All right, so certainly some of this lecture is really good review for things that you're going to see on this exam 2. Remember all this discussion about limits at infinity and asymptotes, that's for exam 3. So the second derivative test, limits at infinity, and our discussion on asymptotes. This is all for exam 3. Will not be on exam 2 that starts later this week. All right, please, please, please come by for help. When I say come by my online office this week, or come by my on-campus hours, which are tomorrow, Tuesday, and Wednesday. Like I said at the beginning of lecture today, come by for help, and I'll be more than happy to help you out as you go into exam 2. Have a great day. Thank you very much.